Imagine a world without electronics. No smartphones, no computers, no televisions. It's hard to picture, isn't it? Electronics rely on our ability to control electricity. Capacitance, the ability to store electrical energy, is a key player in this control. Capacitors are like tiny reservoirs of electrical energy. They are found in almost every electronic device, from the smallest sensors to the largest power grids. Without capacitors, our world would be a very different place. They are essential for everything from smoothing out voltage fluctuations to filtering signals in radios. Understanding capacitance is essential for anyone interested in electronics. It's a fundamental concept that underpins the operation of countless devices. In this exploration, we'll delve into the fascinating world of capacitors, uncovering their secrets and discovering how they shape our technological landscape. A capacitor is quite simple in its construction. It consists of two conductive plates separated by an insulating material called a dielectric. When a voltage is applied across these plates, something amazing happens. One plate accumulates a positive charge, while the other plate accumulates a negative charge. This separation of charge creates an electric field within the dielectric, storing electrical energy. Think of it like stretching a rubber band. You are storing potential energy. The amount of charge a capacitor can store is measured in farads. A farad is a large unit, so you'll often see capacitors with values of microfarads or picofarads. The capacitance depends on the size of the plates, the distance between them, and the type of dielectric material used. Sometimes we need to increase the voltage rating of our capacitors without changing the capacitance value. We can achieve this by connecting capacitors in series. Imagine a chain of people carrying buckets of water, one after the other. When capacitors are connected in series, the total capacitance decreases. It's like having a longer path for the electrical charge to flow through. The formula for calculating the total capacitance of capacitors in series is 1 over C total equals 1 over C1 plus 1 over C2 plus 1 over C3 and so on. For example, if we connect 3 capacitors of 10 microfarads each in series, the total capacitance would be around 3.33 microfarads. The voltage across each capacitor adds up to the total applied voltage. When capacitors are connected in parallel, it's like having multiple paths for the electrical charge to flow. Imagine a group of people filling buckets from the same water source. They can fill more buckets faster by working together. In a parallel configuration, the total capacitance increases. It's like having a larger reservoir to store the electrical energy. The formula for calculating the total capacitance of capacitors in parallel is straightforward. C total equals C1 plus C2 plus C3 and so on. If we connect 3 capacitors of 10 microfarads each in parallel, the total capacitance would be 30 microfarads. The voltage across each capacitor remains the same and is equal to the applied voltage.